Hello, and welcome to my presentation for Lab 3, Magnetic Field of a Bar Magnet. Experiment Background and Principles. In this experiment, in order to calculate the desired values, we will be using the Biot-Savart law, the idea of distance dependence, which means that the observed magnetic field at an observation location varies depending on how far away it is from a magnet, magnetic field of a dipole, magnetic north versus cardinal north, which means that the Earth has a magnetic field which is different and points in a different north than the direction north you would find on a map, magnetic field of a bar magnet, and an axis dipole magnetic field, all of which are illustrated in the equations to the right on this slide. Procedure. Using a smartphone magnometer app, I rotated my phone until the X component is as close as possible to 0 in order to align with magnetic north. Then, we find the location of the magnometer on the smartphone using a bar magnet, positioning it at different areas until we can zero out the Y component. Then we measure the magnitude of the magnetic field of the bar magnet at different distances from the bar magnet. And then we measure the magnitude of the magnetic field of the bar magnet along the 45-degree axis at a distance where the magnetic field has a magnitude of 100 times 10 to the negative 6 teslas. Observations and data. The equation found by plugging in all the different values and distances and magnometer recordings for the different distances from the bar magnet aggregated into equation that equals y equals negative 4.932x minus 17.256. I observed that the further the bar magnet is from the magnometer, the smaller the x component. The closer, the bigger the x component. If the bar magnet is sufficiently far away from the magnometer, the x component reads close to 0. Here is the data from the Excel sheet. As you can see, the equation in the previous slide was taken from the line calculated from the plot of natural log of r versus natural log of the x component of the magnetic field. Calculations. Using the equation found from the Excel sheet, I found that k is equal to e to the negative 17.256, or 3.25 times 10 to the negative 8th. Using the equations found on the experiment, principles, and background slide, I also found that n is equal to negative 4.492, and then setting k equal to mu0 to mu over 4 pi, found that mu, the dipole of the magnet, is equal to 0.1602. Glow script. As you can see in the model from my VPython code, it is consistent with the idea that the magnetic field of a dipole bar magnet will flow from south to north and out and back again. The magenta arrow in the top right corner of the image is the magnetic field at 45 degrees at distance d, with d equal to about 0.53 meters. Reflection questions. The observed magnetic field was negative 1.35 times 10 to the negative 5th, negative 8643 times 10 to the negative 6th, and negative 1.47 times 10 to the negative 4th. As you can see, that is pretty different from the expected magnetic field, which is 5.3 times 10 to the negative 8th, 1.59 times 10 to the negative 7th, and 0. This may have happened because my magnet was not oriented correctly, or it was not put on the right side of the magnometer on my phone. How would results have changed if I hadn't compensated for magnetic north? The x and y components would have changed drastically, the sign of the change depending on the angle with which the phone was with respect to magnetic north. How would results have changed if there were two magnets? The magnetic field would be much larger, about twice as big, because there would be two magnets with the same dipole moment creating a magnetic field. This is the end of my video lab report. Thank you for watching.